Okay. What do we do for this first one here? We need. Okay. So what do you want to do? What's the formula? Okay. So the selenium and the sulfurs. What we got? So we got 18 electrons to deal with. So what are some options we have? Lewis structure wise. So give me one. Okay. What else we got? That's the same molecule. Something like that. So 18 electrons to deal with. Let's mess around with the first one. So how do we manage that to get it to be happy?
You could put a double bond between each sulfurs and the selenium. And that would make the selenium happy. And then put all your extra electrons around the sulfurs.
That's only 16. We have 18 electrons.
You can, doesn't sulfur, isn't it hyper
Yeah, I can have more. So
just throw it on.
Just throw 2 more electrons on this?
Yeah.
Okay. Now what? So, well, let's do the Lewis structures for the other two. There's 18. How about okay. So what about formal charges? Let's do the first molecule. So the formal charge for the sulfur on the left is what? It's this guy here. This one. 6 minus what? What's the 6? Valence electrons. Then what? Subtract what? The lone electrons, so there's 4. And then subtract what? Half the bonding electrons. Okay with that? So there's 4 bonding electrons here. Those 2 and those 2. So there's 4, and then I divide that by 2. So I get a 0 for this guy right here. So a 0 on that sulfur. What about the selenium in the middle? 6 minus what? 0. There's no lone pair of electrons there, right? Minus what? Yeah, okay, 8 divided by 2. And so what do we get? A 2. So a 2 for the selenium. And then what about this sulfur on the end? 6 minus 4 divided by 2? minus 2. So at least the charges work out, right? For this molecule, it equals 0. Okay, so let's check the next one. This sulfur here, I've got 6 minus 4 minus 4 divided by 2, so it's a 0 for this sulfur. This sulfur that's in the middle, it's 6 minus 2 minus 6 divided by 2. 3. So this one here is a 1. And then over here we've got 6 divided by 6 minus 2 divided by 2. So we get minus 1. And this guy down here, what do we get? 6 minus 6 minus 2 divided by 2 equals negative 1. So negative 1 here. And then you got a 6 minus 2. 6 divided by 2. So plus 1 on this guy. And then over here I've got 6 minus 4 minus 4 divided by 2. So I get a 0. So I get a 0 on this one. So which one of these is not, which one of these is the least likely to be the correct Lewis structure? This one here on the left, because those numbers are larger. And then these two here, they're both just as likely. There's probably another Lewis structure for this one then, if I've got both just as likely. We could do, I mean, we don't have anything, we can do another one. How about sulfur, selenium, sulfur, lone pair of electrons, double bond, 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so for this first one, we've done that enough. It ends up being a 0. And then for this one, it's going to be plus 1, plus 1. And then for the last one, it's going to be minus 1. So there are several options for the Lewis structure. So when we get into the several options, what kind of thing do you think ends up happening? These are all the same. Dotted line? Yeah, the dotted line thing. Yeah, resonance occurs. We'll get resonance structures appearing. Okay, so on 361 of the text, find the bond energies, list those values here and explain why they're different. Okay, so 361. So where are we? Nope. Gotta go over here.
I have a question about the formal charges.
Yeah.
Is it okay to, maybe not. I think I did it wrong because I did the whole molecule.
No, it's atom by atom. Formal charges are by atom.
Okay.
It's supposedly telling you what the apparent charge of an atom in a molecule is.
Okay.
And the sum of the formal charges for all the atoms in the molecule need to equal whatever the charge of the atom is. If it's a molecule, it needs to equal what? 0. And if it's an ion, it needs to equal whatever its charge is. So if it's a nitrite, the sum of the two oxygens of the nitrogen had better equal minus 1. So
do you have, sorry, I haven't checked it. Are there worksheets for this sort of thing on the Moodle?
on Moodle? No.
Okay, good. I'm not
Did you post those on those questions out of the back of the text? So the forum, right? So you can find questions like this in the back of the text. So you should post those.
Oh.
There was one that was kind of confusing. I can't say right now, but I'm pretty sure it was better at this stage.
Okay.
I couldn't figure it out.
When we finish with this one, we'll look at it. Okay, so here's page 361, and we're looking for What are the two?
Sulfur bromide and sulfur chloride.
Sulfur bromide and sulfur chloride. All right, so these two values. So the two values are 215 and 250. And can you explain them? Go ahead.
Bromine has less energy because there's a greater distance between bromine protons and sulfur's valence electrons.
So because the bromine itself is a larger atom, it's bonding via its valence electrons, which are literally further away from the bromine's nucleus. And so the distance between the sulfur and the bromine is larger than the distance between the sulfur and the chlorine, so it's easier to bust them apart from each other. Yeah, that's it.
Can we just be like, it's bigger, so this, or is it like valence?
What's the this part? It's bigger.
Valence electron being farther apart.
When you say it's bigger, what is the it's? I guess that's my question.
Bromine is bigger.
Bromine is bigger than chlorine, so
So the valence electrons are farther away from the nucleus.
so
So it has a weaker bond.
you haven't said why though. You're leading me right down the path. You actually haven't said that path right there. What's the one thing he needs to say? It's this, and because of those two things, this is what's going on. The sulfur and the bromine are physically further away from each other. I mean, yes, you're right. The bromine's larger. And yes, you're right. The valence electrons on the bromine are further away from the bromine. All of that stuff is totally true. But because of that, the sulfur and the bromine are physically located further away from each other. And that's what makes the bond weaker. Because everything else is about the same, right? We're talking about a chlorine and a bromine, both halogens, both need one electron. Sulfur, obviously the same thing, so nothing different there. So is oops, don't want that. So this was 215 and this was 250 and this is bigger atom. So sulfur, bromine are farther apart. How is silicon able to form 4 bonds? Explain this using hybridization. Okay, what do we got?
The s orbitals move up into valence electron positions.
I put it into words. It's yeah, I tried to draw a picture.
All right, so if I put the electrons in here, how many electrons do I have in? Yeah, I'll just do it. So tell me about this.
Not interactive
Why?
because it's like neon.
That's neon, right? So those electrons are off limits. So we don't have to worry about those. Just like in carbon, I don't have to worry about the first two because those are heliums. And so now I have 4 electrons to deal with. And what Pauling would have said is that these guys here, we're going to rewrite it. So it looks like S, I'll go 3sp. So why is it like this? Say again? It makes 4 bonds, but why is it okay to put these things at the same level? Like, what is this y-axis here? Energy. So tell me about the energy of these. Very similar. So the energy difference from here to there is tiny, so small that I can have these 4 orbitals hybridize.
So in other words, they bleed into each each other, sort of.
They absolutely bleed into each other. They are literally added together. So in this case, it would be a circle, or sorry, a sphere, plus the dumbbells in their different shapes, right?
Yes. So it actually does make an entirely new sort of shape.
It makes an entirely new shape, and that shape is what? Yeah, all this equals a tetrahedral.
Does that only happen in the 4A column?
No. No, we can get that kind of situation happening with other spots. Okay, this last one here. How do you want to start with this? Yeah, write a chemical equation, right? So hydrogen plus oxygen. Why is that not erasing? Put a 2 right there and a 2 right there. So there's our balanced chemical equation. So how many hydrogen bonds do I have on the left? So we're talking about bonds formed, right? And bonds broken. So how many bonds am I breaking? 3? Okay, so the 3 bonds I'm going to be breaking are what? So 2 times whatever hydrogen is plus whatever the oxygen. What kind of bond is it? It's a double bond. So let's go back over to this guy. So I've got an oxygen double bond. So it's 498 kilojoules for that one. And then the hydrogen bond is 436. So then I'll put 436 here. And what was it, 498? Oh, you guys have? Okay. So that's how much energy it's going to take to bust those guys apart. And then to form it, what am I forming? How about times 4? Because there's 2 molecules being formed. Didn't you just tell me I had to break 2 hydrogen bonds? Okay. So then the hydrogen-oxygen bond is 464. So 464. So 4 times 464 minus 2 times 436 plus 498. 486. So you guys got? Don't remember? What'd you get?
I got 352. That's probably exactly.
Okay, what'd you do? 350. I could get 352 out of that.
So, right, I don't know